Okay. I did some work on the two determinations of the efficiency, or four if you can actually calculate as many as four as one group did. So anyway, I think this will work. There's a hard copy. We're missing somebody.
Dan.
Oh. All right, if you have any questions, contact me, drop by and see me. This has been a long problem, and it goes back before the Agilent analyzers, the old HP analyzers that we used. You could do circuit fit parameters. So the efficiency should have been determined two ways, going way back to Brian. And so they never did it. I don't know why, but I think this should work. So we'll see. All right, so we're going to finish chapter 6 today. And then we have a discussion tomorrow. And there'll be a quiz, okay? And you're working on a quiz right now, right? Okay. All right, so we went through how a design may go. So we saw some aspects of designing sonar projectors, arrays of sonar projectors, or the elements of arrays of sonar projectors. And it's complicated. Typically there are a lot of requirements. But even one thing you need to realize, that even if you come up with the great, perfect design, and you have this thing, somebody makes this, you make it, or somebody makes it for you, it still could fail a requirement. And that's because the specs on piezoceramics is, uncertainty of roughly 10%. So that could cause trouble. Remember we discussed this before, that they just can't manufacture these things to very good precision. So one thing that people naturally do is they make adjustments after the transducer is made, hopefully before it's assembled. Okay, so one thing you can do is, before it's assembled, the measurements can be taken on the piezoceramic to characterize it better, that particular piezoceramic. And then you can make changes before it's assembled. So a simple example is the blocked capacitance. Suppose for some reason you need a precise, a certain blocked capacitance value, and the value is not good enough for you. You can add just a capacitor in parallel in the assembly phase to fix it. As we mentioned, there are a lot of trade-offs here. You can design it to meet one specification and fails to meet another one. So there are trade-offs here. They're contradictory. A lot of them are contradictory. You can't satisfy both. So you just have to settle for something. And I'm sure that all of this can't be done analytically, like we did it. Although we use some numerical results, I think that ultimately, typically what happens is it's shoved on a computer. And apparently there are algorithms to search for parameters for a good design. That's kind of interesting. Okay, so anyway, the final thing we're going to talk about are called very low projector frequencies. This is a frequency of roughly 100 hertz or below. Yeah?
So if the Navy needed 100 transducers of the same type for a fleet of submarines or whatever, they wouldn't all be, identical. They will all each have their own independent quantity.
In fact, you'd be surprised. there are, you can buy precision microphones, and and two of them if you need two. For example, suppose you want to look at the difference voltage in order to come up with a vector sensor. I think we've talked about that in the last. And to look at the difference voltage, you precisely need these two transducers to be the same. And I've done this before, and they were. They didn't have, the sensitivities were the same within 1%, okay? Now that I could adjust with a we adjusted that, we put a potentiometer on it. We tuned that to the sensitivities the same. But what made the thing fail was the phases were different. I have no idea how that could have happened. These were piezo-resistive microphones. Okay, that's kind of weird. It's using, when a sound wave comes in, it stresses the material and it causes a change in electrical resistance. So you can use that to pick up on sound. So the tolerances here are not what you would think. They're not very good at all. And this was a highly precision case. These were expensive transducers. So does anybody know how to shift the phase from a signal? I think there should be a way to do that. So this is going to be one of Faisal's projects. We want to come up with a vector sensor, which the Navy's very much interested in, and they've used all kinds of weird transducers. And I dealt with one of them that was just a disaster. I told you about that, the $10,000 disaster. So, yeah. So what was your question?
It's like all the transducers in the fleet aren't the same, even if their specs are probably very similar.
So the bottom line is, what do you need for some array or something like that? What kind of, how identical do the things have to be? And if they have to be very identical, then you're going to have a lot of adjustments to do once you get these things. So in the case of when you're measuring the voltage difference, it's critical. It's very critical. In other words, when the sound wave is coming here and you're looking at the voltage difference from these two pressure microphones, they better be very nearly identical because you want to pick up 0. You want to just pick up the sound wave coming in this direction. So in that case, it's critical to have identical transducers. Okay, so a very low, this is typically 100 hertz or below. And the wavelength here is 100 hertz is 15 meters. We're talking about big wavelengths here. And the tone pilts geometry, the tone pilts idea fails, and you can see this. I go more beyond what Brian says. I just glanced at it, but we're going to do a sort of careful, what's called scaling analysis there. Scaling analysis. It's quite simple, but it dramatically shows you why there's no point in trying to use a tone pilts projector for very low frequencies. So here's a typical, this is in the book, here's typical properties of tone pilts projectors. Radiating phase diameter, this is 5 kilohertz, 30 centimeters, as we dealt with this previously. Intensity, peak, we're not going to really need these. Total mass is roughly that, heavier than what we were dealing with. And remember, what's going on here is and the idea is quite simple. The transducer is basically a bar of piezo ceramic with two masses on it, and you're looking at the vibration like this, and it's asymmetric. One's heavier, but that's what it essentially is. And there's a uniform expansion and compression. So to try to scale, let's try to scale this up, make it bigger, so that we can lower the resonant frequency to 100 hertz. That's the idea. Here's the formula for the frequency. Okay, we'll use this formula. K is the spring constant, stiffness. M is remember that's the effective mass. It's not going to really be important here, as you'll see. Exactly what this is not going to be important here, as you'll see, because we're just going to do a scaling law here. Now you remember, so here's what we're going to do. We're going to scale the tone pilts up by a factor, the same factor in all three directions. We're just going to blow it up, right? Same scaling, and we'll call the scale factor alpha. So if alpha is 2 and I want to scale this up, It's going to be twice as long and it's going to have twice the diameter. All right? It'll have the same material though. All right? So, how does kappa depend upon alpha? Remember, the stiffness is proportional to the cross-sectional area and inversely proportional to the length. So if I doubled the size of this thing, what's going to happen to the stiffness? Okay, so the stiffness is proportional to the cross-sectional area.
It's less by a factor of alpha.
Okay, I don't see that. Let's go through this. Okay, so let's take a factor of 2. Well, this has a stiffness, right?
Yeah.
We double the diameter. So the area goes up by a factor of 4. Okay, so the stiffness is going to increase. Due to the area, the stiffness is going to quadruple. Due to the length, it halves. So what does the stiffness do? It goes up by a factor of 2. Were you guys saying down?
I said down.
Oh, okay. I think well, no one else is admitting it, but okay. Anyway, so these are scaling arguments are very simple, but they can be extremely useful, okay? So alpha is going to, kappa is going to scale like alpha. What about the mass? Well, that's going to go, it's going to go like alpha cubed, right? Because the mass involves the density times the volume, and the volume is going to go like alpha cubed. If I double everything, I'm going to get 8 times the volume. Okay, so the frequency is going to behave as 1 over alpha. How does the wavelength behave? Well, I just put this down here. It was, I guess in the past this was obvious to me. I don't know if this is obvious, but to be careful here, we can use this. The speed of sound is not going to change. We're not changing the material. We're just changing the geometry. The speed of sound stays the same. So if the frequency goes down by a factor of alpha, the wavelength has to scale with alpha. Now, so the scale factor we need to go from 5 kilohertz down to 1 kilohertz is going to be a factor of 50. And here's what the tone pilts would have to be. It would be 6 meters long, right? Excuse me, it would have a face diameter of 6 meters. It'd be 15 meters long. It would, look at this. That's, mega kilograms. I don't know if that's legitimate, but this is huge, right? It's completely out of the question. So I want to impress upon you, this is a simple argument here. And you always, when you're searching for something like this, you want to think simply and sort of from a physics perspective. Because, for example, you wouldn't want to start making this, say, oh, let's just make it a little bigger and see what happens. It's really pointless, okay? Because this tells us it's just, you need to find a different what we call operating principle. You need to go to something different, plan B or C, and they've done this, D, E, as you'll see, okay? And, 2 words are why, right? Cold War, all the effort that went into this. Okay. So one idea is to use flexural motion. Typically, flexural motion has a very low frequency. The demonstration you saw yesterday, was that yesterday? It doesn't really work too well. Oh yeah, I felt it. It was vibrating. So, these frequencies are typically kilohertz for a metal rod, but if you look at flexure, it's way down tens of, The frequency yesterday was, I don't know what it was, roughly 10 hertz or something like that, with that flexing bar. Something like, it was very low. So that's a natural thing to consider. So there are several of them, we're going to consider these. They're in the book. I found that I've had to add a little bit, okay? And I'll talk to you about that in just a moment. There's just all kinds of strange ideas that have been entertained. We'll talk about this, gas-filled enclosures. All right. Now, I want to mention, in case you get interested or this comes up in your research or whatever, Brian is good about referencing all this. He talks a little bit about these different ideas. And they're almost all JASA articles, Journal of the Acoustical Society of America. And I have just about all of them. I had to get them because I couldn't, for me, he just didn't give enough information for me to understand the basic physics of what's going on. So I have, if you need these articles, just let me know, I can send them to you. I remember I had to look through these just to get the basic idea of how these low frequency projectors, what the basic idea of how they work is. This I mentioned many times before. Okay, so the first one is a flexural disc. And what this is, it's actually called a bilaminar flexural plate. And the idea is this. You have a piezoelectric plate, right, and it's polarized this way. Think this D here, think of this as just giving the direction of polarization. So I got a plate that's polarized this way, and it's electroded that way. Okay? And then I put another one there, the same one, same direction of the polarization, like that. All right? So these two electroplates here they're going to be at the same potential, right? And you can see what's going to happen here. Suppose there's a positive voltage here. That means the electric field is pointing down here, right? This is positive, so the electric field is pointing down here. What's the electric field pointing? Where's it pointing here? Up. Thank you. It's pointing up. Okay, they're opposite directions. So what that's going to do is, with the electric field pointing down, what's going to happen transversely is this is going to, I think, contract. Yeah, when the electric field is in the direction of polarization, it will stretch. Okay, so here, this one will contract, and what's this one going to do? Remember, the electric field here is pointing in the same direction as it will stretch. So we get two actions that are going together. This is a classic example of what's called push-pull. So one is wanting to go like this, the other one is compressing. It's going to want to bend this upward. The other one is expanding. It's also going to cause the bilamina here to flex upward. So it's a kind of push-pull here, working together. Now there's a big problem with this, especially for low frequency. We're interested in low frequency, right? What's the problem? What kind of sound, what kind of amplitudes are you going to generate with this thing? This is a dipole source, right? So when it's going like this, it creates a compression that will propagate. But what's back here? An expansion. And at the low frequencies, there's going to be big diffraction here. So this, you'll get very little intensity out of this thing. You need to turn it into a monopole. Well, it's actually easy to do. You'd get another one, make or get another one. Okay, so now imagine that we have these two ones approximately identical. Okay, they're like this. Okay, and now what I'm going to do is put one like this and apply the voltage, and then we've got a monopole. So, it's not. I guess these lines are supposed to denote the fact that I don't know. I don't know what this means, but you need to recognize here that when the voltage is such that this one's going like this, you want this one to go like that. You want it to be at the mirror image of the other one. And now you got a monopole, a changing volume. Okay, any questions about that one? That's the idea. This one's interesting. This has a particular name, Tensional transducer. And here's the idea here. You have here's the piezoceramic element here. And operated as an expansion bar here, so I guess it's not really critical, as you'll see, but one possibility is it's plated and polarized in this direction, and you got the length expansion and contraction like we discussed. And then this is a non-piezo material here, thin metal, for example. And you can see the idea here is that as this piezo ceramic expands and contracts, it's going to cause, oh, I hit the, God. This expands and contracts, and it's going to go like this. It's a monopole source of sound. And I haven't worked this out, but it seems to me like for a little bit of a displacement here, a little bit of displacement here, it seems like you get a pretty big displacement change here. A pretty, it seems like there's some kind of mechanical advantage here. Now, it doesn't come free. If a little bit of displacement here causes a significant change, some sense of greater, substantial change in volume here, the force is gonna have to be big. But that's usually not a problem with piezos. The force, the displacements are small. That's the problem with piezos. But you can turn the whole thing around, and I think what's going on here is the whole thing's being turned around. Small displacements here can give you significant volume changes there. Now, this is, it's a cross-sectional view. There's two things you can imagine here. If it looks like this, and if it's open here, now you've got now it's not a monopole, right? You're not changing it. So again, if this is going down, you're creating a compression here, there's an expansion here, and they'll tend to cancel. So you need to cap it off somehow, and you can do that in two ways. This could be a two-dimensional structure that's relatively long compared to the dimension this way, and then you cap the end somehow with something that's flexible, so it doesn't interfere with the motion too much. You can do it that way, and there's another way that's pretty obvious. What's that? You see it?
Make it a disc. No.
Yeah.
Would it?
Yeah, why not?
Yeah, let's squeeze it in.
Yeah, I like that. So I was thinking, I'm having trouble with it. Right, so this could be a piezoceramic disc. Yeah, I like that. Also, this could be a rod, and this could be have cylindrical symmetry. This could be the axis of symmetry. Yeah, so there's a number of ways, right? I'll add the disc. I like the disc. I should have seen that. Where are we? Okay, so what I need to do is maybe simplify. I was thinking about this. Just to get a feeling for this possible mechanical advantage thing, where a little bit of displacement here somehow turns into a big volume change. I don't know how to say it. Is imagine these are close down here and consider this squeezing a little bit. What kind of volume change do you get there? There's got to be a way to get at this. But it just looks like there's some mechanical advantage to this, getting significant volume changes for not that much of a displacement, but I don't know. Here's another thing that people have done, okay? Imagine you have a piezoelectric cylinder you're going to use to send as a projector. And the way we've been talking about it, it needs to be shielded. We'll talk more about this later in the course, but it needs to be shielded from the water somehow. But basically, we think of the water being the outside, and we think of air as being the inside. You can flood it, and they do this. You can have water on the inside. Now, of course, there's details. You need to protect the material especially in saltwater environment, but let's not worry about that, okay? The idea is that by putting water in there, we've increased the inertia and we can lower the resonant frequency. However, we've increased the stiffness, right? So, Brian doesn't talk about that, and I just didn't, I couldn't get deeply into these papers. It takes too much time. But anyway, apparently, the added inertia beats out the added stiffness. I'm suspicious about that, but this is commonly done. Maybe you guys have ever heard of this before? Flooding a piezoelectric cylinder. So it just, okay, what I'm saying is, I think it's done because the way Brian talks, the way the language is here, it's they have a nice word for it, you know. So I think this has been done. I don't know how routine it is, but there are competing effects here. You're adding the inertia, but you're increasing the stiffness. So presumably, the inertia effect beats out the stiffness. Now this is interesting. If you imagine you have a cylinder here, and you flooded it in order to lower the frequency, what happens out here? Well, if it's open, now you're back to this dipole source kind of thing, or actually quadrupole or octopole, I don't know what it is here, but you don't have a monopole source, okay? So you would want to somehow cap off the ends, okay? With some kind of flexible material. And then what happens when you go down deeper and there's greater pressure? If you seal this off, right, and the pressure gets greater, what can happen? The pressure is greater now here, right? And this has been sealed. What can happen? This can crush, exactly. So what do? It's pretty obvious. And nature did this for us a long time ago. You have a little bleed valve here, a small valve, that won't interfere, that won't be any kind of acoustic cancellation. This is too narrow. The viscous penetration depth, if you know about that, is too small. This is just a small bleed valve to equalize the pressure, right? And we all have this, right? It's called, for us, this is our ear, and this is called a eustachian tube. So you're all familiar with that, right? To equalize the pressure. So you can do a similar thing here. It's kind of interesting. Okay, this is weird. This is some kind of elastic material with a gas in it, air. And so it's going to be like a bubble, and it's going to have a resonant frequency. And the resonant frequency is going to be low because there's a lot of inertia. There's not a lot of stiffness here compared to water for a bubble, but this is a big bubble too. But you've got a lot of inertia due to the water is going to be moving, okay? So it's loaded like that, mass loaded. So the resonant frequency can be quite low, and then you just need to drive it on resonance. So they attach some kind of, essentially a moving coil type driver, a shaker. A shaker is essentially a moving coil. Okay, I need to correct myself. When people do earthquake analysis, okay, of scaled up systems, they're not using moving coil. What are they, low frequency like that? You've seen tests like this, right? How are they driving that? When they have a experimental room, you know, with dummies and chairs and stuff like that, and they shake it around. How are they shaking it? They need huge forces, and it's low frequency. It's hydraulics. They're using hydraulics, okay, pistons, cylinders. But on smaller scale, shakers are they're loudspeakers. And we have a number of them. I have several myself. I've used them a lot in research and demonstrations. They're essentially a moving coil, just like a loudspeaker. So you can use that to drive this. And let's not forget, you know, remember Helmholtz resonators? The basic idea of a Helmholtz resonator is you've got this resonator that has a certain size and it's resonating at a wavelength, the wavelength for resonance is much bigger than the size of the system. So it's not a typical standing wave resonance. It's different. It's a Helmholtz resonance. And they're everywhere. So you have a Helmholtz resonator. We think of it as being in air. It's in a fluid. That fluid can be water. There's nothing that stops you from having a Helmholtz resonator in water. And in fact, there are some bays and some harbors that act like, when we're looking into this, not right now, but we're going to, right, guys? The Bay, have I talked about this before? The Bay of Fundy? Did I mention this to you guys? That apparently is a quarter. The Bay of Fundy, which is somewhere over on the east coast between Canada and the United States, has the biggest tide change height elevation on the planet. And it's like, I don't know, 15 meters or something like that. It's huge. Why is it doing that? Anybody know?
The resonant frequency of those basins.
Oh, yeah,
matches the tide.
Dan's Canadian, so
Yeah.
you know.
I grew up just down the street.
Oh.
Not just down the street, but I spent summers there.
Okay, so go ahead. So it's kind of long and narrow, it seems, if you look at it on the map.
Yeah, it's sort of, but the period of the tide matches some multiple other resonant.
Yeah. Oh, I don't know if it's I assumed it was the fundamental mode, but I guess it. Yeah.
Yeah, it's somehow
So we would call it a quarter wavelength resonance. If it is, that's the standard thing. When you have an open closed pipe, right? There's a quarter wave resonance. You know. Okay, go ahead.
So in the different bays or different areas, just by the shape of them or by their location, then they drain, and the height is ridiculous. It goes
Yeah.
from being this lake or an inlet to being completely.
Yeah, it's very dramatic.
Boats drop and sit on the mud for
Yeah.
6 hours and they float again.
Right. So we have one paper that, so that's I think that's a quarter wavelength resonance. You can also have a Helmholtz resonance. And a good candidate is the San Francisco Bay, right? It's got this narrow, it's got this neck. It's actually more like an orifice. Okay? But for a Helmholtz resonator, you don't need a physical neck. Remember that? So I showed you guys, I demonstrated this in a previous course. We had this sphere, it was about this big, it was plastic and gray and had a 1-inch diameter hole, and I blew across the top. So there's very little thickness here, but there is an effect due to the incorrection. You remember the fact that the flow doesn't equal, the pressure doesn't equalize here. You effectively have a neck just due to the flow there, and we actually calculated that in the previous course. So this is what we call a neckless Helmholtz resonator. It's physically neckless, but there is effectively a neck. And so the San Francisco Bay, it's going to have a Helmholtz resonance frequency. Apparently, it doesn't coincide with the tide, that frequency. You know, because otherwise we would all know about it. It'd be like the Bay of Fundy, or maybe even worse. So we have one paper where someone, a famous fluid dynamicist, John Miles, he calculated it for a harbor, for some harbor, right? We haven't really looked at the paper. Have you guys looked at it yet? I haven't looked at it. I just stumbled onto it, so we saved it. Yeah, so natural candidate for low frequency sound because the wavelength is typically much bigger than the size. So that's what we want. So people have done different things. They've taken spheres like this with a hole in it, and this is piezoelectric material here, and they drive it, right? So you can imagine it's plated on the inside and outside. You might wonder, well, how do they do that? We can't, I don't know, okay? But what I think has happened is they can make hemispheres and plate them, you know, and then they can attach them like that to get a sphere. So you're changing you can drive this by changing the volume here. You can drive it, and there's going to be a Helmholtz, there's going to be a resonance there. They've looked at another thing. I mentioned 3 possibilities here. The piezoelectric sphere, a piezoelectric cylinder, okay, and you can cap this off. You can have you can do this, and the piezo material is actually in the cylinder here. Okay, the cylinder is going to go like this. And so it's similar to that. And then probably a more typical one is it's easy to imagine these things. You can have the active piezo could be here. You need to get a volume change here. Well, yeah, I don't even really think about this. Well, okay, how about this? I don't think this is going to be practical, but you can imagine something like this, where that's the piezo. And when after a few times going through this, what hit me was something that I know well about. And that is that you may not, this may surprise you, you may not want to drive this, whatever it is. I don't like that. Let's look at this one. You may want to drive this at twice the resonant frequency rather than at the resonant frequency. Does anybody know why? Okay, look at this. This is a pendulum, right? If I drive the support back and forth, there's resonance, right? I can feel it. Okay? Now this is the standard of the normal we call direct excitation. And if you want to understand it, we need to use Einstein here, believe it or not. We need to go into the frame of reference where the pivot is not moving, okay? So once you imagine going to this frame of reference, going back and forth. You're accelerating back and forth. So what you feel in that frame of reference is not just the Earth's gravitational field. You feel this effective gravitational field going back and forth. You feel a force pushing you back and forth. It's the same thing as if you're in an elevator, and the elevator is accelerating upward at 9.8 meters per second. How do you feel? You feel twice as heavy. You would be, probably difficult to stand up, okay? So there's an equivalence there between a gravitational field and an accelerated frame. That's called the equivalence principle. So if we go into the frame of reference where this is going back and forth, the pendulum here feels this, not just the gravitational force of the Earth, it feels this oscillating gravitational field here due to our accelerated frame, okay? That's the standard case. That's boring. Now, what if you do this? And kids actually naturally do this, okay, for example, on swings. In some places, children don't sit on the swings, they stand on them. And when they drive themselves, what do? They go like this. What they're doing is they're changing the moment of inertia. They're changing a parameter upon which the frequency depends. And when we do this, so this is like a kid going up and down on a swing. You'll notice how this thing it started off slowly and then just took off. This kind of excitation has completely different properties than this, the direct excitation. It's called parametric excitation. Anyone ever heard of it before? It's in our nonlinear, because our nonlinear course has nonlinear oscillation waves. I have a whole chapter on this because I have expertise in this area. So what's happening here is that in this frame of reference going up and down, you're modulating the Earth's the effective gravitational field is being modulated compared to the Earth. It's increasing and decreasing. As you go up, G is greater. As you go down, it's less. The frequency of the pendulum depends upon that parameter. And any time, or just about any time, you have any kind of an oscillator and you modulate a parameter upon which the frequency of the mode depends, you can feed energy in. And one of the amazing things about it is it grows exponentially, and only a nonlinearity can limit the growth. If you had a purely linear oscillator, the amplitude would diverge. And there's a report in the literature from decades ago from the Russians that they took an LC circuit, a linear LC circuit, modulated they did it several different ways. It was really not well reported. You can't reproduce what they did. Okay, and that's, it's a Russian thing, yeah. So this was a long time, this was during the Cold War. So they were probably worried, they didn't want to give out enough information. But They took an LC circuit, highly linear, modulated either the I think in one case the inductance, in one case the different ways. And they got parametrically excited oscillations, and they just kept growing. And before long, what happened? It burnt out, the circuit burnt out. The current was so great that it melted. The wire melted, okay? So, if you modulate this at twice, what's the frequency here? You'll notice that when my hand goes through one cycle from here to here. What has this gone through? A half a cycle. You want to drive at twice the frequency. So if you ever see a kid going up and down on a swing, they're going up and down at twice the frequency of the pendulum. You can achieve parametric excitation in other ways, but that's the fundamental, the best way to feed energy in. So it would be interesting, and I don't know if anyone's ever tried this, it would be interesting to drive this at twice the frequency. You're modulating the volume here. And the possible uses of this is that you can achieve large amplitudes. Now it doesn't come free, you got to supply the energy, but again, piezos are very strong, can generate a lot of forces. So I had a PhD student, one of my PhD students at my previous university, we tried to do this with acoustic. We had a Helmholtz resonator in air, and we tried to parametrically excite it. We worked very hard, and we were unsuccessful. And the reason was, to get, first of all, one possible solution to this is just the thing not moving. Okay, the issue is this state stable? And it turns out it's not stable. You need to give it a little kick, but there's always fluctuations around. I'm driving a little too fast. You can see it's taking off here. There is a threshold that depends upon the quality factor. Due to dissipation, you've got to be above a threshold. Below that threshold, you don't get anything. It just stays in this state, 0. We were not able to get above the threshold. We worked very hard at it. We wanted to get loud sound. We were after loud amplitudes. And one of the applications would be thermoacoustic refrigeration. You can use sound to refrigerate. That was a hot topic back then. It's still being researched, just not as hot. I don't know if hot's the right word for refrigeration, but anyway, that's what we were after. I don't need to demonstrate this. You heard this last quarter, right? Just a couple more here. This is kind of weird. It's a collection of pistons and motors, probably converting rotational motion into oscillatory motion. The old Industrial Revolution thing, right? Like locomotives. Yeah. There you want to convert this into that, right? So it's essentially an underwater loudspeaker. Oh, there's another one here. This one I've heard. I don't know if this is very popular, but this one I've heard a little bit about. You have some kind of flexing plate, okay, that's going to generate the sound, and you hit it with a stream of water, okay, but you pulse the water. So you drive flexural motions with this pulse stream of water. That's the basic idea. So how do you pulse the water? How do they pulse the water? Well, there's a valve in there, and it's actuated by a piezoelectric element. This is interesting that, it looks like we have nothing to do with, we don't need to deal with piezo ceramics here. But to get this pulsing, the way they do it is they typically will do it, at 100 hertz or whatever. They'll do it with piezoelectric. I don't think that's interesting. Now, finally, this one. Here's the last one. This is a spherical shell made out of piezoelectric elements. It's not very low. Its range is actually, it's in this range, okay? But it's interesting. And here it is. This is from the book. Here's a picture. All right. So Channel Industries, they've been in business a long time. Here's this sphere. It's made of basically thickness vibrators, okay? Consider that are triangles. So they covered a sphere. It has a diameter of 30 inches. Okay, this is pretty impressive. It's going to be heavy. So these are all piezo ceramic thickness vibrator triangles here. And one of the things that's interesting about this is you can't really cover a sphere with, they look like equilateral triangles. You can't cover a sphere with, that's not going to work. So somehow they put these things on here. You'll notice they have some filler material in here. You can't just put all these triangles together. It's not going to work. You know, you're going to end up, it's just not going to work. You're not going to be able to cover the whole sphere. You're going to have big problems. So you can see it looks like there's some kind of filler material here, right? And they've just kind of gone along and placed these things and somehow managed to roughly uniformly cover this sphere. That's an interesting problem in geometry just to try to do this. And I don't think you want to just start out and start gluing all this stuff together, because eventually you may find that things don't line up, right? So they probably did some kind of testing or some kind of mock setup before they actually glued all this together. Now, so that's interesting. I think that's interesting. But the really interesting thing is the guy, okay? So I want to point out the white shirt, the thin black tie, the cheap cigar with the built-in holder. When I grew up, these dime a dozen. This guy's out of the 1960s, okay? This guy, and yeah, it's just, to me, that's what strikes me about this photograph is. Yeah. Okay, so anyway, tomorrow the problem set, right? And I hope this works for this. This will finally clear this up. It should have been cleared up a long time ago, before I ever got involved in this course with Lab 3. So let's hopefully, if you guys have any problems with this, make sure you come by and see me. And it was Mark and Stilson and Savas that sort of triggered me into this, how they analyzed the data. So hopefully this will work, and we'll see what these efficiencies are. If you have any questions, come by and see me, okay? And then if this works, then I'm going to revise the handout. Finally, we'll get this done, get it done in a better way than before. Okay.